Hello and welcome back to Elementary Algebra. I am your instructor, Amy Fuchsteiner. We are still working on Chapter 8, which is Radical Expressions. We're going to be looking at 8.3 today, which is how do you simplify radical expressions. We're going to use the product rule. We're going to use prime factorization. We're going to talk about how to simplify square roots when there are variables in them. And then we're also going to use the quotient rule to simplify square roots. We already kind of did the quotient rule, but that's okay. We'll go over it again. As a just sort of side note, my brother's dog, Ozzy, is still with me here today. He is currently sleeping on a blanket in the back. Yeah, it's 3:00 in the afternoon. Yeah, he's only 6 months, 7 months old, but he's really a pretty low energy pup. I'm really enjoying my time with him. All right. And we took a long walk this morning. So there's that too. Okay, so the product rule for square roots is actually something that I already kind of showed you. Bad me. We've been using it. The product rule for square roots says if you have the square root of A and you multiply that by the square root of B, this will be the same thing. It has to equal the square root of the product. So we're going to be using this little fact, which we kind of already did last time. In this unit, right in this section right now, and we use it a lot. We're going to use it throughout this. So we're going to use it to simplify our square roots. When is a square root in its simplest form? 3 big ideas. There can be no perfect squares remaining in the radicand. So no more, you can't take another 25 out, you can't take another 16 out, you can't take another 9 out. No other perfect squares are factors of the radicand. No fractions appear in the radicand. So when there are fractions in the radicand, we want to eliminate those. And lastly, when our denominator, if we have a fraction form, our denominator must be an integer. So it must be a whole number, no more square roots in the denominator. All right? We're going to practice using the product rule and our knowledge of perfect squares. So how do we do this? We look at something like the square root of 28. And it's probably best, let me get my list. There we go. And it's probably best if we use our list of perfect squares. So I'm going to pull out here. I'm going to ignore everything else. I'm going to pull out this list of perfect squares. Okay, I'm going to put it at the top. So here's my listing of perfect squares. I've got the first 24 perfect squares. Do any of these go into 28? So is 28 divisible by 1? Always. That one's not going to matter. Is 28 divisible by 4? It is. So I'm going to rewrite this as the square root of 4 times the square root of 7. Because 28 is 4 times 7. Since I have the product, I can break it into the square roots of the factors. Then I can say that 4 is 2. The square root of 7 will not simplify, so I can leave this as 2 square roots of 7. The square root of 28 must be equal to 2 square roots of 7. And once what's underneath the square root is only divisible by 1 in itself or by 1 and some other number that is not a perfect square, I'm done. Okay? Let's look at problem number 2, the square root of 70. If we're doing the square root of 70, 1 doesn't go into 7. Well, 1 will, always will. 4 won't, 9 won't, 16 won't. 25 does not go evenly into 70. 36 doesn't, 49 doesn't, 64 doesn't, and now I'm bigger than 70. So that's as much as I can do. The square root of 70 is already simplified. There's no more I can do there. That's good. That's it. All right, let's try number 3. This is the square root of 500. Well, right away my brain goes, won't 100 work? It will. The square root of 500 would be the square root of 100 times the square root of 5, because 5 times 100 is 500. I can take the square root of 100, that's 10, and I cannot take the square root of 5, so I will just leave it as 10 square roots of 5. That's as far as I can go, and I'm done. What about the square root of 242? Well, 242 is closest to the 256. So I know it's not going to be any higher than this guy. So 225 won't work, 196 won't work, 169 won't work, 144 won't work, but look at 121. 121 will go, right? So this would be the square root of 121 times the square root of 2. Because if I take turn your calculator, 242, and I divide that by 121, yep, I get 2. So this would be 11 times the square root of 2. Why 11? Because 11 squared is the 121. And that's it. Here we go. That is the product method, using the product rule for the square roots. That's how you would use that. Now, product rule is not a favorite of mine. And basically, it's not a favorite of mine, not because it's bad, but because the product rule sort of leaves you with this guess and check idea, right? Where you're guessing and you're checking all of these square roots that you may or may not be aware of. I may not be aware that 13 squared is 169. So I would never think to look for 13 squared, right? That's why it's not a favorite of mine. I prefer to use the prime factorization method. And the prime factorization method uses that little index trick that we did last section. And it works really well. So here's the idea. The idea with prime factorization is that if you have something like, let's do 128. So if I do the prime factorization of 128, we know I do it a little bit differently. I'll divide by 2, that's 64. I'll divide by 2 again, that's 32. I'll divide by 2 again, that's 16. That's 2 times 8, that's 2 times 4, and that's 2 times 2. That's how I do my prime factorization. So 128 is 2 times 2 times 2 times 2 times 2 times 2 times 2, or 2 to the 2, 3, 4, 5, 6, 7th power. Right? So 128 is 2 to the 7th power. So if I need the square root of 128, remember, what's the index on a square root? The index on a square root is a 2. This would be the square root of 2 to the 7th. What's the index on a square root? 2. We never write it, but we just assume. Do you remember last section? I said, okay, this could be the same as 2 to the 7 over 2. Well, 7 over 2 is 3 with a remainder of 1. So this is 2 to the 3rd with 1 2 remaining underneath the square root, or 8 square roots of 2. Now, why do I prefer this method? Because when I do prime factorization, I can start somewhere, right? And because it's square roots, I know for every 2 underneath, I can pull 1 out. In a slightly modified version, 52 is 2 times 26. 26 is 2 times 13. So this is 2 times 2 times 13. I see that there are 2 2's, or 2 squared. So the square root of 2 squared is a 2, and I'm left with the square root of 13 underneath. So this is 2 square roots of 13. Oops, I wanted to include that. Okay, I'm not doing the prime factorization this way. I'm just sort of doing it in my head. If you wanted to, you could do the prime factorization in any method that you liked. The square root of 140. 140 is even, so I can divide it by 2. That leaves me with a 70. Right? I can do this on my calculator. I can do it in my head, but if you need to, you can do it in your calculator. That's 70, which is still even, so I can divide this by 2. That leaves me with a 35, which is 5 times 7. So this is 2 times 2 times 5 times 7. This is a square root. And since I have 2 2's, I can pull a single 2 up front, and I'm left with 5 times 7 inside, or 2 square roots of 35. Because we would multiply that 5 and 7 back. If I'm doing the square root of 28, this would be the square root of 2 times 14, which is 2 times 7. So 2 2's mean a single 2 can come out, square root of 7. 95 is the square root of 5 times, let's see, 95 divided by 5 is 19. 5 and 19 don't break down any further. Since I cannot break it down any further, I'm just going to leave this as the square root of 95. It is already in simplest form, so I am good, and I'm not going to go any further with that. Right? We can do the same thing with the variables. So y to the 5th, the square root of y to the 5th. Now, 2 different ways using this method. This is an index of 2. So this would be y to the 5 over 2, which is y to the 2 and a half, or 2.5, right? So I can have 2 full y's outside, but I have a remainder of 1, so I need 1 y left on the inside. Y squared times the square root of y. If you like that way, that's great. The other thing you can do is that this is the square root of y times y times y times y times y. There's your y to the 5th, right? So for every 2, because it's a square root, you can bring 1 out. So I can bring out a y and another y. This one, which does not have a pair, needs to stay underneath the square root. So this is y squared square root y, which is exactly what I had before and works perfectly. Okay. 40x squared, that will be the square root of 40 times the square root of x squared. Well, the square root of 40 is 2 times 20, which is 2 times 10, which is 2 times 5. The square root of x squared is x. Right? Square root of x squared is x. So since I have a pair of 2's, I can bring a 2 out front. The 2 times 5 needs to remain underneath. So this is 2 times the square root of 10 times x. This is a problematic way of writing this problem, only because people can't tell if the x is underneath the square root or not. So what we do most of the time is we take this x and we put it between the 2 and the square root. Just to be clear that it is not underneath the square root, we would write this as 2x square root 10. Right? You maybe have noticed also as we've gone along that I always make the little tails, right? See all those little tails that I put on those? Most people don't do this. This is an old school trick. And by old school, I really mean old school. I mean like my high school math teacher who probably had algebra in the late 50s or the early 60s. So this little trick of putting the tail on there is really something that they used 60 plus years ago, 60, 70 years ago. But it's really nice because it really does sort of indicate the end, like past this point, don't include anything underneath the square root. So it is one of my favorite sort of tricks to use for clarity. at least for me. Okay, couple more. Here we have the square root of 50 times c to the third. This would be the square root of 50 times the square root of c to the third. The square root of 50 is going to be a 2 times 5 times 5, or 2 times 25. The square root of c cubed is c times c times c. So if you have a pair, you can bring it out. So that means that here I can bring out a 5. So I have 5 square root 2 times, here I can bring out a c, because I've got a pair of c's, c square root c. So putting it back together, what's on the outside can get multiplied together, 5c. What's underneath the square root can get combined, 2c. So this is 5c times the square root of 2c. Right? Problem number 12, we have the square root of 12, x to the 5th, y to the 9th. So this would be the square root of 12 times the square root of x to the 5th times the square root of y to the 9th. Sorry, lost that. 12 would be 2 times 6, which is 2 times 3. X to the 5th would be, I could pull 5 x's. That would be an x to the 4th times x if I wanted. Y to the 9th, since it's a square root, I need evens. That's going to be a y to the 8th times y. So this will be a 2 square root 3 times an x squared square root x times a y to the 4th square root y, or 2x squared y to the 4th times the square root, everything underneath can get combined, 3xy. Whew. That one was a lot. Let's try the next couple. I think they're going to be pretty similar. So this is going to be a negative 3 times the square root of 32 times the square root of r cubed. Negative 3 times the square root of 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2, times r to the 3rd, which is r times r times r. Okay, I got a pair, I can pull one out. I got a pair, I can pull one out. This can be a negative 3 times 2 times 2. Notice that negative 3 is multiplying, so I'm just keeping that negative 3 along. It's just coming along. Now, I'm going to have a square root of 2 left times r squared. I got a pair of r's, so I can pull out an r, square root r. So negative 3 times 2 times 2 is a negative 12. That r can come out, and the 2 and the r are both underneath, so I'm going to leave them underneath. There we go. All right. How we doing so far? I got a 5x to the 3rd. Then I got a square root of 8 times the square root of x to the 3rd times the square root of y. Well, that square root of 8 I can simplify. So I've got a 5x to the 3rd. I've got a square root of, you can do 4 times 2 if you want. You can do 2 times 2 times 2 here, times the square root of x times x times x, times the square root of y. So I can bring out a 2, I can bring out an x. So 5x cubed times 2 root 2 times x square root x times, nothing I can do with that square root y. Oh, I need an x there. Nice catch. All right, so if I multiply the 5 times the 2, that's 10. X to the 3rd times x is x to the 4th. And then I've got a 2xy all underneath. There we go. 10x to the 4th times 2xy. Bam. Great. Okay. Beautiful. Fourth part, use the quotient rule to simplify roots. The square root of a quotient versus the quotient of square roots. Oh. The square root of a quotient, which is a over b, all of this underneath the square root must equal the quotient of square roots, the square root of a over the square root of b. Now, the crazy part is we've been doing this. This is the quotient rule for square roots. The square root of a over b must be equal to the same as the square root of a over the square root of b. All right. Again, we are assuming a and b are positive, right? Because we can't take negative square roots. So we're going to go ahead and assume a and b are positive and b cannot be 0 because we can't have 0 in the denominator. So what does this look like? I think we already did some problems, but let's just take some simplifications here. Here's some examples. Here we have the square root of 20 over the square root of 20 over 81. This is the same as the square root of 20 over the square root of 81. Now, the square root of 20 is the square root of 2 times 2 times 5. The square root of 81 is 9. And yes, if you know the square root, don't worry about it. Just stick it in there. So this would be 2 square roots of 5 over 9. Remember that the 2 times 2, the pair of them indicates that 1 can come out because that would be 4. The square root of 4 is indeed 2. The square root of 300 over 4 would be the square root of 300 over the square root of 4. We do know the square root of 4 is 2. The square root of 300, I'm going to do this because it comes to me as the square root of 100 times the square root of 3. That's 10 square roots of 3 over 2. And look, do you see how that cancels? So this is going to be 5 square roots of 3. Every once in a while, somebody will say, but Amy, couldn't I have divided underneath? Yep. In this particular case, you could have. You certainly could have. If you would have, you would have gotten the square root of 75, which, by the way, would be the square root of 25 times 3, or the square root of 25 times the square root of 3, which is 5 square roots of 3. Same answer, 2 different methods. Both work. All right, here we have the square root of x to the third over 9, which would be the square root of x to the third over the square root of 9. X to the third is x times x over 3. A pair means I can bring 1 out. So we'd have x square root of x all over 3. Well, I didn't box that one up top. I'll do that. All right, problem 18. We have the square root of 150h to the 5th over j to the 4th. So this would be the square root of 150 times the square root of h to the 5th over the square root of j to the 4th. So 150 is 2 times 75, which is 3 times 25, which is 5 times 5, times h to the 5th would be h to the 4th times h, and j to the 4th would be j squared. So this is going to be, the pair here means I can bring 1 out, 5 times the square root of 6 times h squared, square root of h, over j squared, which is going to be 5h squared times the square root of 6h all of this over j squared. Beautiful. Beautiful questions. We're good. Okay. All right. So for number 19, I have the, look at, I can cancel. A to the 5th over A to the 4th is just going to be an A. And B to the 7th over B squared is going to be a B to the 5th. So this is really a square root of AB to the 5th, which would be the square root of A, that's 1, times the square root B to the 5th would be a nice B to the 4th times B. So I can pull out a B squared, and then we're left with square root of A times square root of B, which is going to be B squared, square root AB. I like that. This time I simplified first, and that's all right, because I could. And if you see it, you can simplify that like that. That's fine. All right, problem number 20 is the square root of 32x to the 5th over 2 over 9y to the 4th. I don't see anything that simplifies here, so I'm going to do the square root of 32 times the square root of x to the 5th, breaking apart the factors of the numerator. And then I'm going to do the square root of 9 times the square root of x to the 4th. Now, in the numerator, 32 is 2 times 2 times 2 times 2 times 2. And x to the 5th is going to be x to the 4th times x. And this is going to be 3x squared. So I can pull out, a 2 and another 2. So 2 times 2 is 4, square root of 2, times x squared, square root of x. Oh, that should be a y, shouldn't it? How do I change that from an x to a y? I don't know. I just get on a tear sometimes. So that's going to be over 3y squared. So we're going to have a 4x squared times the square root of 2 times x over a 3y squared. How do I know it's in simplest form? To recap, there are no perfect squares underneath the square root. 2 is not a perfect square. X is not a perfect square. That's the first thing that cannot happen. There cannot be perfect squares remaining underneath the square root. There are no fractions underneath the square root. There are no fractions remaining here underneath the square root. And there cannot be any radicals in the denominator. Both of these are non-radicals. There are no more square roots. We have an integer and a value of y, whatever that may be. All right? So I know this is in simplest form. If I want to check the next, I can check any of them in here. If I check this one, I cannot simplify. There's no more perfect squares underneath the remaining square root. There are no fractions underneath the square root. Yes, the whole thing is a fraction, but there's not a fraction underneath the square root. And my denominator is not a square root. Done. How do I know this is simplest form? What's underneath the square root cannot be simplified any further. In other words, there's no perfect squares underneath the square root. Done. There's no fractions underneath the square root. Done. This whole thing is a fraction, but the fraction is not underneath the square root. So this qualifies. Any denominators are not roots. So this is not a square root in the denominator. Done. Okay? 3 ways to know that you have a radical in simplest form. Right? There is some practice in this, actually quite a bit of practice on this. If you have any questions about anything, please don't hesitate to reach out to myself or to the Math Center. We are all happy to help you. We are here if you need us. And until then, we'll see you next time. Thanks.